However, for the brute force solver, for the brute force n-body solver, the application was able to scale either for one GPU and for both for one GPU and for two GPUs, which proved that the scaling is not limiting scalability and the other applications are not scaling for other reasons. The Barnett algorithm has scaled either one GPU or with two GPUs, depending on the workload size. For bigger workload sizes, it was worth to use two GPUs, otherwise it was not. Some conclusions, I have a lot of conclusions in the paper, but some conclusions in the presentation. Well, the state-of-art frameworks to address heterogeneous platforms does not cover irregular applications. And irregular applications are a big slice of applications. We have a lot of algorithms that work on graphs, on trees, and those are considered irregular. So it is very important to develop a framework that can handle irregular applications on heterogeneous platforms. The scheduling on these environments is very hard because of different reasons, as I told you, and this is especially relevant in irregular applications. As a side conclusion, if you want, we just realized that heterogeneous platforms are only appropriate to specific algorithms. If our algorithm does not have high ratios of computation per memory access, it is not a good algorithm. And obviously, if our algorithm is designed to work very well on one device of that platform, as it was our FFT version, it is not worthwhile to use heterogeneous platforms with other devices because an efficient scheduler will not just use the other devices, right? The proposed model was able to efficiently handle irregular applications, in particular parts of the algorithm, by achieving levels of efficiency that overcame 100%, which is the ideal case. And that's all. Thank you very much for your attention.
Okay, sorry if you told it and I missed from your presentation, but I wonder what is the granularity of your scheduling? I mean, what is the minimal you told task which gets scheduled? I wonder about the basic application flow, how it is divided on those tasks, whether this is a programmer task to define these pieces which are gets scheduled, or is it done somehow automatically or something?
Yes, you have to specify a dicing method which basically divides your workload into several tasks. And the number of tasks and the amount of computation per task is entirely up to you, up to the programmer. I admit that will have impact on the scheduling efficiency, obviously. And for an expert program, it can turn irregular applications on regular ones, and with that dicing method, and that would be even better.
I see. So the sampling is done based on this programmer-defined tasks, right?
Right.
Okay, thank you.
Just a short question to this one. So, in the case of the bonus tree code, what was this measuring with this task, this piece of running code or whatever?
Do you mean the measuring of the execution time of each task?
Yes. So what was a task? That's calculating with
Yes, it was the net force calculation.
So a total force calculation for the whole system, for all the modules.
Yes.
And you just repeat it many, many times? So?
Yes, 30 times, I guess, or 25 at least.
Okay, thank you.
Thanks for the question about your performance model. So, how much information is the programmer supposed to provide you about his tests or computations? So, your framework runs a sample test to measure the performance, and after that, how is that data interpreted in context of a concrete test that should be executed and which is a real test? So, how is the performance model applied to real data? How much is the program supposed to help your framework with that?
Those are in fact two questions, right? Okay, regarding the first one, how much information has a programmer to give to the platform? The answer is no. Okay, you have quite no information to the platform. What we are doing is actually labeling a small part of the workload as sampling tasks. Okay, like 20% of the application's workload is labeled as sampling tasks. Those tasks will be the first to run, and their execution time will be recorded and used to fit the performance model. Okay. Your second question was how the performance model uses that data during the application lifetime, right? It basically do the median of, for example, if you run five tasks that belongs to the same kernel, they are in fact the same task. Okay, their domains might be the same, and in that case, we run the tasks and we calculate the median of those tasks. Okay, and we record just the median and use just the median as an estimation for the execution time. Nevertheless, you might define tasks according to the Dyson method, and it is a shame I did not show the Dyson method, but it would take a lot of time to explain every part of the process. But if you define, as our colleague was telling me, your tasks with different domains, which is basically, imagine that you have a vector of 1,000 units, and you define your task as doing a unit increment on every position. Okay, and the first task will increment a unit on the first 5 positions. The second task will increment the unit on the 10 next positions. So those tasks will be different because the data domain are different, right? Our performance model is able to estimate the execution time of one task with regard to the length of the data domain of that task. Is the question answered?
Yeah, so as far as I understand it, the programmer is supposed to provide some kind of range abstraction.
Exactly. That's not considered information. That's part of the
programming model.
Exactly.
Okay, I see. Thank you.
I was wondering if it's, as I understand, it's libraries of an application, so I use this application and it's in application scheduling. And so if I run, for example, 2 applications with this framework, what will be with the scheduling and how it will divide the tasks between cores and...
2 questions again. The second question, if you run 2 applications, how is the schedule? Well, we provide synchronization points like barriers, and you basically define one entire application to run a synchronization point and the second application. Okay, so the scheduler will actually schedule the workload until the first synchronization point, and try to minimize the execution time of the first application, and then it tries to minimize the execution time of the second application. So basically the framework, I would say that the framework is focused on minimizing the execution time of one application only, okay? Because between synchronization points it tries to minimize the execution time of the workload that might exist between those synchronization points, but after one synchronization point the scheduling process starts again.
So I understand that framework is separate from the application, or it's inbuilt in this application. How
No.
it's used? I don't quite understand how your framework is used in an application.
Okay, your first question from the other term was about libraries. Just to make it clear, you can use libraries, in fact, but in the general case, you will download the framework and write C++ code, data parallel code on the framework. So basically, you define your entire application. But just to give you an example, imagine that you're running the Saxby algorithm with the vector 1,000 positions. You might define your task as resorting to external libraries like LaTeX, or Cuplus, okay? But you're entirely responsible for designing your application and to define what tasks compose that application. Actually, I don't have the code to show you, but it is straightforward.
Yes, but the question is about, for example, high-performance computing clusters, where we have a scheduler that schedules and it gives you some amount of nodes, the amount of computing power, so you have several cores, some amount of memory, and you and I, for example, start several applications based on your framework. And it has its own inner schedule.
Okay.
So how will divide this part of course of the main clusters?
The first thing about our framework is that it is designed to work on one node, okay, without networking. So in a cluster, it just doesn't work. It works on a node only. Also, schedulers for clusters and for the majority of clusters are based not on reducing the execution time of one application, but increasing the occupancy levels of the cluster. The goals are just different. As I told you, in our definition of scheduling, schedule is the act of assigning computational tasks to devices targeting a given goal. In the case of clusters, the majority of them, and I've been studying the literature about this, is to increase the occupancy at best because of the costs of building one entire cluster. And I can show you that those kind of scaling algorithms are not good if you intend to reduce the execution time of your application. So